Welcome back students. Today in this video we are going to talk about Bernoulli's theorem, and as you can see here it is written that it is based on law of conservation of energy. So we know that law of conservation of energy states that energy can't be created nor it can be destroyed. It can be just converted from one form to another. And as we are talking about the subjects of fluid mechanics or hydraulics and its applications in civil engineering, the fluid or the liquid that we will generally consider will be water. Okay, so let's see that what this theorem states. So it states that in a case of steady ideal flow of an incompressible fluid, the total energy of the fluid at any point is constant. Okay, and this total energy comprises of three kinds of energy: pressure energy, kinetic energy, or potential and potential or datum energy. Okay, so according to this theorem, what it is trying to say, it is trying to say that when your fluid is flowing in an open channel or a pipe, then at any point the summation of the three type of energies, that is pressure energy, kinetic energy and potential energy, at any point or at any section will be same or will be constant. Okay, and these energies are expressed as energies per unit weight of fluid. So mathematically Bernoulli's theorem can be stated as P by rho g plus V square by 2g plus Z, and this is the total energy which will be constant at any point of the fluid. Okay, and here P by rho g is known as the pressure head, V square by 2g is known as the velocity head, and Z is known as the datum, and here P is the pressure, V is the velocity. Okay, so the pressure energies, kinetic energy and datum energy are expressed in terms of energy per unit weight of fluid, and mathematically they are represented as this. Now let us try to understand the application of Bernoulli's theorem or what we have just seen through an example. So here you can see one figure. A pipe section is drawn, and within that pipe section a Venturi meter is connected. Now for your information, Venturi meter is the application of Bernoulli's theorem and which is used to find the discharge through pipe. Okay, so that how we can calculate the discharge through Venturi meter, that we will see in our next video or lecture, but right now let us understand this theorem through this figure. So this is the section of a pipe, and in between this pipe this Venturi meter is fitted. Now with this Venturi meter, as you can see, some glass tubes are connected, and as we have seen in our previous videos, these glass tubes are nothing but they are piezometers. Okay, so let us consider that Q is the constant discharge which is flowing through this pipe. Okay, and when it will flow through this pipe, there will be variation in the pressure at the different sections. Okay, where the Venturi meter is connected, because as you can see the cross sectional area in this Venturi meter is changing. So Venturi meter has three components. The first component is converging section, the middle one is throat, and the last one is diverging section. So along the three components these piezometers are attached. So let us see that how this pressure will variate. Okay, so if I consider this section, so at this section you can see the cross sectional area is somewhat more, and as it is moving ahead the cross sectional area is decreasing. So at this section, as the cross sectional area is more, the velocity will be less and the pressure will be high. So you must know that velocity is inversely proportional to pressure. So this relation you must be aware of. Okay, so as the velocity will be less, the pressure head will be, the pressure will be more. Okay, and if I am coming to this section, okay, let us see at the second section also. So at this section the cross sectional area is somewhat less as compared to this section. So the velocity will be somewhat more and hence the pressure will be somewhat less. Now coming at the throat section, so here there is a measurable difference in the cross sectional area, and hence as the cross sectional area is less, the velocity will be more and the pressure will be less. And similarly, as we are moving toward the diverging section, the cross sectional area is increasing and accordingly the pressure will variate. Okay, now here as you can see a datum is considered. So with respect to this datum up to the central line of pipe, this is the central line of pipe. So from the datum up to the central line of pipe, Z will be there, which is known as the datum head. From the center of line of the pipe up to the point where pressure will be there, that will be represented by pressure head, which is P by rho g, and after that, as the fluid is in moving condition, it will also have some velocity head, which is represented by V square by 2g. So the total energy of flowing fluid will be Z, which is datum head, P by rho g, which is pressure head, and V square by 2g, which is velocity head. Okay, and as you can see that as the pressure head is changing at different sections of the Venturi meter, as the cross sectional area is changing, the value of P by rho g will be different at different sections, and so the value of V square by 2g will also differ, and the value of Z will be same for all the sections, as the datum which is considered is same. So when we sum it up these three values, that is Z plus P by rho g plus V square by 2g at any section, its value must remain same, as it is based on law of conservation of energy. So here what will happen, that at section 1 the value of P by rho g will be higher, but at section 2 the value of P by rho g will be less, but alternatively at section 2 the value of V square by 2g will increase, while at section 1 the value of V square by 2g will decrease, as the pressure and velocity are inversely proportional. But when we sum it up, so at section 1 and 2 or at any section, the summation of these three values must remain constant. So that is verified, or that is the verification of Bernoulli's theorem that could be achieved through experiments in laboratories. Thank you.